Hi, today we're gonna talk about auto-vectorization. Auto-vectorization is a fantastic technology, right? It's when the compiler takes your scalar code and rewrites it as SIMD code. We already saw this example. This is doubling every element, right? And post-Clang in GCC can vectorize it. And yes, sure, we had some issues with how GCC vectorizes it, like it can be about a third faster, but I'm fairly certain that compared to scalar code, this is about 8 times faster. Right, so about a third is maybe not that important. Right, and when the compiler auto-vectorizes our code, it's fantastic because we don't have to write the intrinsics. We don't have to use like crazy libraries, and we can easily convince our coworkers that this small rewrite that improves our performance substantially is worth doing. Unlike I'm fairly certain for many of you, like bringing a new library would be a tough sell. Okay. To be fair, right, compilers are not magic. They do roughly what you would do, right? So they rewrite the scalar code with SIMD and they do it with available SIMD, right? So here I'm compiling for SSE 4.2 and for IVX2. The same code, and we can see that the intrinsics are very different. A compiler didn't do any dynamic dispatch based on the architecture we have, or anything else smart. All right, so we still need to provide correct compiler options, right? We still need to know which architecture we target or which architectures and then select and runtime the correct one. That's the performance difference on my machine. All right, the more modern architecture, IVX2, is about SIMD extensions, not architecture. But it's about 2 times faster. Okay. So, important thing, we need to understand what can be auto-vectorized. And I went online. I found a few lists, right? There is a GCC nodes, LLVM nodes, and there is our favorite 0x80 block. However, all of them are not complete, and I think kind of like a bit random. So I created my own that is also not complete, but follows this following idea. That I at least think, right, based on observation, not based on reading code, that the way vectorizer works is by pattern recognition. It has certain patterns built in, right? And it knows that this scalar code matches to this SIMD code. And if it can match your scalar code to one of the existing SIMD patterns it has, it will rewrite it. Otherwise, it will leave it as is. And so we'll go with the patterns first, right? So the first important pattern is transform-like. We already saw double all of the elements, right? But here I wrote it not with standard transform, but with a while loop. And you can see the result is still the same, right? Basically, what I'm saying here is that it doesn't matter how you write your loop. If it matches the pattern, should be good. We can use more than one array, like no problem. Here I'm using, 2 arrays. We can do some more tricky, like this is still not adjacent difference. It's also a transform, effectively. It subtracts m plus first element from n's element, right, and writes it to the output. The other way around. Like from n plus 1, you subtract n and write it to the output. However, this is what I mean by pattern recognition, right? This way, it writes it like this with a lot of shuffles, like this. It moves a lot of elements around in the vectors. If I rewrite it as transform, all right, it does a completely different SIMD code, and it's actually much closer to what I would write, at least without measuring anything. Like I don't know which one is faster, but this one I would write. This one is closer to what I would write. However, what I'm saying is that it's a pattern recognition. You can try to mess with your code and see if maybe you can change it slightly so that you get the vectorization you want. Okay, this is an interesting example. This example of replace, right? And if you use standard replace, it will not be vectorized because standard replace has an if in it, and if condition is true, right, it will write. If condition is false, it will not write, and compiler cannot introduce a write. Like that would be, that will mess with you. So here but here we do the ternary condition, and the ternary always writes, so compiler can write, and then we get we get the vectorization. Good stuff. So standard converting from one type to another, right? Many people think of copy as vmCPI, but this is not quite always the case. If your types are different, right, you need to convert between them, and the compiler can do it for you, right? Filling the value, right? Just if you want to fill the array with a given value, no problem. Swap ranges, right? It's like it's a transform, but you don't write to one range, you write to two. No problem, compiler can do it for you, right? This is a vectorized. IOTA, like this is interesting. This is working with indexes. Compilers can work with indexes a little bit. Like IOTA is writing 0, 1, 2, 3, 4, right? And yeah, compiler can do it, and it's actually vectorizing it quite nicely. And another one that is like transform is combining just a range with indexes. We can do. Alright, so for example, here I'm multiplying the element by an index, and the compiler vectorized it, which was great.